know about each other. Okay, so I should say it's really a pleasure to see many familiar faces, and I thank those of you who are already here early in the morning, and maybe some of the others watch this as a recording. Okay, I'll start with something that is quite well known. It's the Heisenberg uncertainty principle, but I will already early try to put it in a slightly different context, namely in the context that is given by the title. And one important word of the title is this quantum in front of agents. So usually when we use quantum mechanics, we are of course talking about quantum systems. But in my talk, it will be important that actually the users of the theory, the agents, so an agent for me will mostly be a user of the theory, are quantum mechanical as well. But let's first start with the traditional picture where we have, let's say, a normal agent, which we usually implicitly think as a classical person in the sense that will hopefully become more clear during the talk. But I think we all understand somehow that we are classical, at least our thoughts, the way we process information is pretty much a classical machine, if you think in these terms. Now, the Heisenberg uncertainty experiment or principle could be illustrated in the most simple case by the measurement just of a single spin system. So assume that we have here a system S that is, let's say, a qubit or a spin, and then there is a measurement device here, and this measurement device leaves us an option. We can either measure in the X or in the Z direction. So we can either measure spin up, down, or right, left, and we get an outcome, either X or Z. Now, you probably, if you learned quantum mechanics in the traditional way, you probably learned about Heisenberg's principle as a relation that is phrased in terms of some variance that is bigger than h bar times something that depends on the commutator of the observables, but there is also an information theoretic formulation of the principle. And in the case of a single qubit or a spin system, this formulation, and in the case of X and Z measurement, so that's a very particular case, and I'll only talk about this case today, we can write it in terms of an entropic expression. I mean, this also generalizes to more complicated systems, even to continuous ones, but I'll only talk about this very simple case to illustrate this. So this H here is the von Neumann, or no, not von Neumann. So X is a classical thing. So H is the Shannon entropy. That is well known from information theory. So what this tells us is that the uncertainty we have about X, about the, what does it mean to have an uncertainty about X? So there is this measurement, and of course the person who prepared the experiment knows the state here. So this could be an arbitrary state, phi, could also be a mixed one if you like, and this person could now ask himself, how much do I know about the measurement outcome? And so this quantity is the uncertainty he has in the case where he would do a mixed measurement, and that's the uncertainty he has when he would do a Z measurement. And it's pretty obvious. I mean, you can easily verify this in special cases. If the person, of course, prepares, for example, a spin to the right, then he knows the X measurement will tell him the spin is right. So there's no uncertainty. This term is zero. However, the complementary term, the measurement in the other direction, Z, is of course, maximally uncertain, so this entropy here will be 1. And this equation tells us that, however cleverly you try to choose this state to minimize the total uncertainty, you will never be able to actually reduce that below 1. Okay, that's a very well-known result, and I think I will now not give references because it's actually coming out of a sequence of a very long development that took place long before my time, of course, started by Heisenberg. Now, as I said at the beginning, this word quantum is very important. So let's now try to see how this experiment looks like if we think of this person here. So the person was implicit so far, but let's suppose this is now a very elaborate agent, one that can can process quantum information. So it's someone who has some knowledge, K. And K could in general be a quantum system. So what does that mean? How can we generalize this thing? Let's for the moment just reflect how we could as well express the inequality that is here, still in the case where K would be restricted to be a classical value. So in this case, we could just write the same equation as X, or the inequality as h of X given K plus h of Z given K is larger or equal to 1. So if K is classical, what this means, it's just the average entropy of X conditioned on whatever that knowledge is. And of course, if this inequality holds always for any classical knowledge, then it also holds in that sense if I average over the possible knowledge here. So that's still kind of a classical statement here. But now if you really think of this as a quantum machine, for example, a quantum computer that uses quantum mechanics, then it's very natural to say that K is not necessarily a classical value. And so these entropies here have to be generalized. And this is not something we have to now invent. We know very well what it means to talk about the uncertainty about still a classical value X. So the outcome of the measurement will still be classical, but conditioned on knowledge that is quantum mechanical. So information theorists have studied this, and this is not just a mathematical expression. Mathematically, by the way, we could write it as h of xk minus h of k. So you can express it as the total entropy you have about x and k together minus h of k. And you could say, okay, that's just a mathematical equation that doesn't tell us much, but information theorists can show that this quantity corresponds to the amount of bits you would have to learn if you already know k, so that you're able to reproduce x. So you can really interpret this operationally as the number of bits that you're missing or lacking until you would know x. So by an optimal scheme. So you could ask for these bits and then you know x, and the same here. So this is not, in quotation marks, merely a mathematical thing, but an operationally relevant quantity. This is, of course, important if you want to claim things that are somehow relevant, because, of course, we can write down whatever equations we like, but the question is, do they have anything to do with physics? So this one clearly has. It's telling us exactly this thing. However, what we also know, and this is also nothing new, is that if in the extreme case, and one extreme case would be that this observer that I've drawn here would now not prepare a fixed state in some way, but would be entangled with the quantum system. So that's also a kind of knowledge the person could have in the quantum sense. So the knowledge consists of a qubit that is, let's say, maximally entangled with the spin system here. So I'll write this down. So in case K and S are maximally entangled, we can look at these entropies, and it's not surprising, given also the operational meaning of those, that they are now zero. So both h of x given k and h of z given k are equal to zero. So that's consistent with the operational meaning that I just mentioned before, because clearly if this person is entangled with S, whatever measurement would be done, the person could perfectly know what the outcome is for both possible measurements. So this means that this inequality here, so the information theoretic version of Heisenberg's uncertainty relation, is not valid in general. It's only valid if we make an additional assumption about K, and this is an assumption we would, of course, naturally make without even talking about it, namely that the knowledge K is classical. But I think the point of this kind of introductory part is really to tell you that whenever we make statements in quantum mechanics, we are usually implicitly making the assumption that we are looking at the world from the viewpoint, from a classical viewpoint. We are classical, and not all the statements we are making in that sense are valid if, or would still be valid if we were ourselves quantum mechanical. Certainly not this statement. But there's a more interesting aspect to this. I mean, this is somehow the starting point. You could say, okay, this is now no longer true, but is there still some interesting inequality that in a reasonable way generalizes Heisenberg's uncertainty principle? Because you could say, okay, that would have shown us Heisenberg's uncertainty principle is just an artifact of the fact that we are classical, but not really fundamental. But this is not true. There is actually a version of Heisenberg's uncertainty relation, which still makes almost this statement, but in a slightly different way, and is again completely generally valid. And this is also still stuff that is kind of known since several years. Let me state that. So the difference, and this is, I think, really the interesting part, is instead of talking about classicality, we could talk about the shareability of information. So let's suppose now that we have two agents here outside. One has knowledge KA, so this is the agent A, obviously, and the other agent has knowledge KB. And they both have knowledge about the same S. This S is again going to be measured either with respect to X or Z, and someone can choose, and you're just asking yourself, how well can you predict these things for either choices? Now the statement that can be shown, also there's a more general version in case they're not only qubits, but the statement that is generally true is now the one that looks, first of all, identical to the above. I'll have to add something, so it looks like this, but the important addition is that I put here a little index A and here a little index B. Of course, I could also, I mean, symmetric, it's also true for the other direction when I put B here and A here. So what this tells us is that, or I mean, this version of Heisenberg's uncertainty principle tells us that while it's true that a single agent could actually know the outcome of both possible measurements perfectly in that sense, that is entropy is zero, and if there are two agents, they could not somehow share this information. They could not, for example, arrange that one of them knows X and the other one knows Z. It could still be that one keeps all the information. Let's say A just stays entangled with this system S and doesn't give anything to B. But in this case, of course, this quantity here is 1 and this one is 0, but the inequality still holds. But there's no way they can somehow subdivide the entangled qubit they would maybe have initially, that is entangled with S, into knowledge Ka and Kb, so that each person knows one of the values. So in other words, this very valuable information that allows you to break Heisenberg's uncertainty principle, seemingly, in this naive formulation that I've given here, this does no longer work if you have two persons who want to share information. So you could say that the more general way of phrasing Heisenberg and the actual limitation is not a limitation that comes from classicality, but it comes from the shareability. So in other words, Heisenberg's uncertainty relation tells us we cannot in general share information in such a way that we know everything in the sense that there would be 0 here. Okay, so this was still kind of an introduction, and the introduction was had the purpose to tell you that there is, I mean, actually two purposes. One is that it's not unnatural, in particular today when we talk about agents which could be quantum computers, to think of agents holding quantum information. And the important aspect is these agents never make a measurement of their own brain. That doesn't make sense. So a quantum computer just stays quantum. So you couldn't say, okay, this is true, but the agent would still have to really know X. The agent would have to measure his own brain. No, the agent is just quantum mechanical. And what this means is that he has a mechanism in principle to reproduce X, and he has a mechanism to reproduce Z at the same time. I mean, at the same time means he cannot communicate it, but he knows it internally. He could answer both questions. So the other purpose was really to make this connection between shareability and somehow make the claim, which is also something that is very well known to quantum information theorists, that classical information can be shared, That's very easy. That's what we do when we talk, whereas quantum information cannot in general be shared. There's also the no cloning principle. So one can interpret this also as making a connection between Heisenberg's uncertainty and no cloning principle, or even saying it's actually the same if you see it in that way. Okay, but if you look at now this connection between shareability and classicality, we could also ask somehow the opposite question. So do we really understand, or we could ask ourselves, when is it still true that the classical reasoning that we are usually applying, and by usual I mean when we're doing stuff like deriving the conventional Heisenberg principle, when is this still valid? Because after all, we are in a quantum world, and we could say, at least if we take the perspective of someone who says that decoherence is not fundamental, but it's just leakage to the environment, so somehow the overall evolution is always unitary. In this picture, of course, the world is always quantum, and we could ask ourselves, why is it then true that in certain situations we can do as if we were classical? So what's really the criterion that we are classical? And one criterion could exactly be that we can kind of share information. Okay, now after this introduction, I would like to make a little jump and just discuss briefly how, in this view, experiments that we know of, or thought experiments, in particular those which are close to my heart, namely Wigner's friend experiment, look like in this picture. So the picture actually looks very similar, but I'll just have a different title, namely Wigner's friend. So we have again an agent. Let's call him Wigner, and he has some knowledge, K. Oops. And now instead of actually just doing a measurement of the spin himself, he lets a friend do this measurement. That was, of course, the famous idea of Wigner. So there's a friend in a lab, F, and this lab is, if you like, perfectly closed. And now you could ask the friend, for example, to make a measurement in the Z direction, let's say. And that's usually what you do in the Wigner's friend experiment. Now, and for later purposes, I want to think of this as the outside observer, W, the Wigner, somehow injects a spin system S into the lab. So he prepares actually the spin in the lab, and then the lab is perfectly closed, and the friend starts with the measurement. Now, the typical thing, or the typical way the Wigner's friend experiment is done, is that the state that is prepared, let's say the state phi S, is a superposition between up and down, and I will just call that spin right. So that's just omitting normalization factors and spin up, down, or we could also, of course, equivalently take a spin left, and I would define this as being a superposition with a negative sign between up and down. So that's just a convention that I'm using. Let's now make a slight change to this Wigner's friend experiment. So usually the Wigner just prepares that state here, the spin right, and then asks what would the friend get, or then is this whole discussion about the friend being in a superposition between seeing up and down. So the friend clearly measures in the up-down basis, in the Z basis, and you would expect he sees up or down. But we could also say that Wigner sometimes inputs that state, and of course the conclusion is the same. The friend will sometimes be in the measure see up and sometimes down. Now, as I think many of you know, there was an extension of the Wigner's friend experiment, a very clever extension by David Deutsch. He actually extended it in two ways. One part of the extension was to say that the friend, after having performed the measurement, confirms that he has done the measurement and that he has seen a single outcome, and he tells that to Wigner without actually revealing what the outcome is. So it's important that he doesn't share this information, because of course the coherence would be destroyed between the two outcomes. He just confirms, I've seen one outcome, but I don't tell you which one. The other thing one can do, and which was also done in Deutsch's version, is to somehow apply a measurement in a big superposition basis. I call this measurement an X hat measurement. So X is like the measurement in the basis that corresponds to the state. So one basis state is the state of the entire lab if the input to the lab was this spin here, the spin right, and the other basis state of this measurement is the entire state of the lab if this state here was input. So in other words, if Wigner decides to provide this state, then the final outcome here of this measurement from the outside will be actually that it was this state. So it will say with certainty it was the spin right state, and the same for the spin left. So it's kind of a confirmation that the lab is still somehow in the state one would expect it to be if the evolution was unitary. Now the important point in the Wigner's friend thought experiment is that we have somehow an apparent contradiction if we think too classically. And the apparent contradiction, which was already pointed out by Wigner, is that clearly the friend here will see an outcome, for example, up. But from Wigner's viewpoint, this whole system, because it's closed, and assuming that evolution is unitary, will be in a superposition of the spin being up and the friend having seen it's up, and the system being down and the friend having seen it's down. So we have seemingly contradictory statements. And Wigner could even confirm that his state assignment is correct by, as I said before, by applying this measurement. So the situation is now in information theoretic terms. In the conventional case that Wigner, if we ask ourselves, what does Wigner know about the final measurement provided from the outside to the lab, given whatever he knew at the beginning, and at the beginning he knows which state was prepared, whether it was prepared in this one or this one. This knowledge is such that he has no uncertainty. So in other words, Wigner can perfectly predict what comes out here. On the other hand, in this conventional experiment, Wigner has no information about the outcome of the friend. So Wigner thinks it's equally likely up or down, independently of whether he prepared it in this state here or in this state here. Now let's, as before, move to quantum information. So let's somehow turn this K into a quantum K, make it in blue, and now I write things in blue. So this is now just the quantum Wigner. This is now the deviation from the usual way of thinking. So we now assume that Wigner is a quantum person. And of course, now instead of preparing either right or left, he could again, as before, as in the Heisenberg experiment, just prepare a spin that is entangled with his own knowledge. And then, as we have seen before, for exactly the same reasons as before, he still has, of course, the same, at least the same knowledge as he had classically, so he can perfectly know what the outcome here would be. But now, because he's perfectly entangled with the spin, he also has perfect information in this information theoretic sense that I explained before about what the friend will measure. So this is now kind of an interesting perspective on the Wigner's friend experiment. We have now a Wigner, a quantum Wigner, who knows with certainty what the friend will see. So in particular knows somehow that the friend gets a single value, because in particular knows the value, again in this information theoretic sense that he could reconstruct, he could tell what the value was, but he also has knowledge about the outside measurement here, or the outcome of this outside measurement. Now, one remark about this is that if you think back about the development of interpretations of quantum theory, for example, many worlds, this was of course strongly motivated by this situation here. So many worlds is clearly motivated by the fact that from Wigner's viewpoint, there is this superposition between two possible worlds, one in which the friend sees up and one in which he sees down. But now you could say that if we were quantum agents, we would never have come up with the many worlds, because from the quantum agent's viewpoint, it's just perfectly clear what the friend has. There's just one value. So one could, and that's maybe a provocative statement, and I don't want to dwell too much on that. One could say many worlds, the whole interpretation that came out or the many worlds interpretation is an artifact of implicitly assuming that agents have classical knowledge and want to bring things back into that classical picture. But in a fully generic quantum agent would have been in that situation and not come up with the idea that there could be these parallel things. Now you could of course complain and say, but from the outside it's still an entangled state. But of course you could recursively continue in that way and say there could be even an outside agent who has in the same way full information about this inside scenario and so on. Okay, so that was the kind of provocative remark. Now I want to actually come back to something which is maybe not provocative, but more a challenge. Because all what I've shown now is kind of to illustrate that if you make this step from the usual assumption of we are classical and we are describing the world from this classical perspective to a new kind of view where we say, no, agents can themselves be quantum mechanical. When we make this step, certain things that we are kind of used to, for example, as I said, uncertainty relation, or that there are these branchings of seeming apparent branchings of the world, they look very different from this quantum agent's perspective. So, okay, I always feel, I mean, I don't want to kind of say that this is anything new so far. I just want to put that in a new perspective. And I'm very well aware that many of you have, of course, are extremely familiar with this. I mean, in particular, of course, I want to mention actually Czeslaw Bruckner, who is all the time talking about quantum agents with his whole research program on quantum reference frames. And I think one could even say that this is somehow the information theoretic analog of that. So if you look at it from a more physical perspective, you should also say our reference frames from whose viewpoints we talk are actually also quantum systems. So that's the consequent continuation of this approach. And that's why I really very much appreciate these research programs going to quantum reference frames and so on, and that have been started by some people here in the audience. Okay, so now I want to somehow ask the question, and that's the challenge: when can we be certain that we can still argue in the usual way? Because most of the things we have developed are actually based on this implicit assumption that we are looking at them from a classical perspective. So that's kind of the question: when is the, I call it classical agent reasoning, and still justified? So one answer could be never, because in principle we are here living in a quantum world, and that would be the perspective of someone who certainly wouldn't believe in a objective collapse mechanism, and I also don't believe in that. So we would say clearly the evolution is unitary, and decoherence is just that certain information gets inaccessible to us, but viewed from the outside, everything is quantum. And so therefore, this notion of classicality is not fundamental at all. And we should always ask ourselves, we should never trust in this notion, because ultimately we are not classical. Okay, I see there is a question in the chat. I think, let me see what it is. From Nicola. Okay.
I don't know if you want to answer now or at the end. That's up to you.
Yeah, maybe that's a more philosophical. I mean, what does it mean that the quantum agent knows? I think this is an extremely important question. Let's for the moment, and let's come back into the discussion, but let's for the moment really just say it's in this information theoretic sense that the agent with knowledge K knows that if this quantity here is zero. And I said before, there is an operational meaning to that. So I can at least, it's not only a mathematical statement I'm making, it's kind of an operational one. The question is, of course, is it a statement we really want? But that's, for the moment, let's say, our working assumption that we have a good information theoretic understanding what it means, which has this operational significance.
But the operational significance that you gave us is for classical agents. I don't see the operational meaning for a quantum agent.
So then maybe I wasn't clear. So the operational meaning is that if I'm an agent with, I mean, let's suppose I was a quantum, or okay, I'm not quantum, but let's suppose there's a quantum computer with the knowledge K, and I would now, I mean, this thing means how much information, or in general, I mean, if it's zero, it's different, but if I have this, then this quantity, whatever this number is how much information would I need to provide to that agent, to that quantum computer, until the quantum computer is able to tell me with certainty what the value set is. But so this is really quantum. Of course, the answer from the outside is then, I'm certain that the value is this, but this K here is a quantum system in general. So the question is, how much do you need to add to that quantum system until the knowledge about Z is kind of contained in these quantum systems, in the sense that the agent could now answer the question and tell me what Z is. So it's kind of a game, tell me what Z is. And if you can do it, then your uncertainty is zero. If you can do it with probability 1. But I know that this is, I mean, as I said, this is not a trivial point, and I'm also not sure it's the best way to see that. And I would suggest we come back to that in the discussion session.
Okay, thank you.
Okay. Now back to this question: when is a classical agent classical agent view still justified under which situation? So, as I said before, to put that in formulas, let's suppose we have an agent, as before, and the agent now somehow is really classical in the conventional sense. So what does it mean we are classical in the conventional sense? There is some decoherence. So a classical agent knowing a value X, one could characterize from the outside viewpoint, or the quantum state from the outside viewpoint would be the following, that the agent, so let's, okay, for the moment assume that X is now just some value. It's now independent of whether it's a spin or whether it's an outcome of a measurement. So let's suppose X is a value, 0 or 1, and we could now ask ourselves, what does it mean that an agent knows X if the agent is classical? And here's the very familiar thing that we would say, the agent, let's call the agent now for the moment A, knows 0 in some way. And then there is also an environment of the agent, which is also somehow in a 0 state. So this is the environment. And the actual system X is 0. So this is really the system X. But there could even be a situation where there is this superposition, that the agent knows it's 1, the environment is in a corresponding 1 state, and the X system in 1. In this situation, which is clearly a quantum situation viewed from the outside, so again, I dropped normalization factors, but this is clearly a superposition state. We would say from the agent's viewpoint, or this is actually a classical agent, because the agent's information about X has completely leaked to the environment, so it's kind of copied to the environment, and therefore, if we trace out the environment, we get the familiar classical state. We would say, okay, that's maybe a characterization of what it means to be classical for the agent. But as I said before, of course, it's a quantum state. And if you look at things from the outside, it's quantum. Now, what could be the criterion here that it can be written in that way is not a very useful one. Because if I now know something, for example, I know that if I look out of my window, the weather is very nice, blue sky, that's knowledge I have. But can I therefore, how sure can I be that this is classical knowledge? Of course, what I could do is to ask myself, how does the situation look like from the outside? And then maybe come to the conclusion that me, with my knowledge and the weather outside together is in a quantum state where this information I have about the weather is copied. But in general, this is very hard to do. So in general, we don't know what the state of the universe is. And in order to somehow decide whether my own knowledge is classical, I don't necessarily want to take an outside perspective. I would rather want to have a criterion that somehow tells me that that I have classical, or that my knowledge can be treated as classical without taking this outside perspective. And so one candidate for this could be that we would say, let's just say that if we are certain about something, then this is kind of classicality. So in other words, if my assignment of a value x is that I'm sure the value x is, for example, 0 with probability 1, then one could say, okay, that reasonably means that from my perspective, this knowledge is 1. If I could, for example, also verify that. So let's look at this situation again. So let's suppose I have now a quantum system S, and I know it's S. I should write it like that. So suppose I know S is in state 0, for example. Then what I can do is I could, in principle, verify it. So this is verifiable in the sense that I could just apply a measurement. And we know that this measurement will not even change the state. So I could apply projective measurement, and the state of the system S is still 0. So this seems to be a very strong way of saying I'm really sure something has the value 0, and therefore I could consider my this thing to be somehow classical. And that's what we usually assume. However, and that's maybe the final point I want to make before posing the challenge, this is not generally going to work. So if you're saying classical reasoning is justified, whenever we are only reasoning about things which we are certain about in the sense that they are in principle verifiable without disturbing the system. So that's even close to kind of Einstein's view of what it means that something is real, that I can, without changing the state of the system, verify or confirm it. And this is clearly the case, as I said here. I mean, if I know it's 0 and I project it in the 0, it's still in the 0 state. So are we safe in this situation where we can verify things? And my answer to this is no, we are not. And the reason for that is again a Wigner's friend thought experiment, and not surprisingly, it's the extension of the experiment that I proposed together with Daniela Frauchiger, which is, by the way, quite similar to the experiment proposed by Czeslaw Bruckner, but there's exactly an important difference in this aspect, that all the information that the agents have in this thought experiment is information of the type that they are certain about something. I don't want to really go through the experiment right now. That would require much more time, and I think I'm only 5 minutes or so left. But I just want to give you a flavor of what this experiment does for those who haven't seen it, and tell you in what sense it tells us that even that definition of classicality is kind of problematic. So the experiment is essentially consisting of 4 agents. And I kind of now give a very high-level view of it. There are 2 agents, which are called A and B. And these agents are allowed to communicate. So they're agents like this. They can somehow exchange quantum information. For example, A can send something to B. However, otherwise they're completely isolated. So apart from this information that they can communicate, they are in boxes that are shielded, that shield them from the environment. But there are also other agents outside. There are 2 more agents. And these agents are, let's call them U and V, or W for Wigner. And these agents have the possibility to measure the entire labs, like in the case before, when in Deutsch's version of the Wigner's friend experiment. And they get certain outcomes. For example, W could get an outcome that I also call W. Now, the whole point of this thought experiment is that the setup, I mean, all the agents are kind of instructed to do certain things. For example, the agent A has to do something, let's say measure some random bit, and then depending on the outcome of the random bit, send something to Bob. Then U is instructed to measure A in a particular way, and W is instructed to measure in a particular way. Furthermore, all the agents are instructed to make a prediction about or to make a statement about the final outcome. So this measurement of W on that lab is a measurement that is done at the very end. Now, the experiment proceeds in such a way that A, so there's like different times, and at time A, at time 1, agent A prepares something. He has some value, which I call R. And he can sometimes make a prediction with certainty. So for example, the statement is that if R is a coin which can take, let's say, values, heads or tail. Let's suppose if R is tails, then, so that's a statement that A makes, then A is certain about the following. He can say, I'm certain that W takes a certain value, and let's suppose W takes values from the set OK and fail. These are just two outcomes. And so the experiment is arranged in such a way that A can sometimes make this definitive statement. He doesn't communicate it, but he just makes it for himself. A writes it down. He has this statement. And then there's a chain of statements that the other people can make. So B also does some measurement. In the experiment, he measures the value Z, which can take values, let's say, plus or minus. Okay, it's actually better to write it up or down. Sorry for that. I want to be consistent with what is actually in the paper. So let's say it's U or D. And now we also have the statement that if, for example, Z is U or up, then B can make a statement, and the statement B can make is, I'm certain that, for example, R is equal to tails. Now, you see, these are exactly the statements that are certain in the sense I said it before. So in principle, the person could go there and measure the state and do a projective measurement on the state, and that projective measurement will not change the state as seen from the party's viewpoint. So in that sense, it's really something that he could be very confident about, to somehow be classical in that strong sense that it's verifiable. Now the point is that in this experiment, these agents now proceed by reasoning, which is somehow the reasoning that we are used to do when the world is really classical. Because clearly, if you are B and you can make this statement that you're certain that R is tails, and you also know, I mean, that's something you can infer, that if R is tails, A made this statement, then B can make another statement. He can make the statement, I'm certain that A is certain that W is equal to fail. That seems safe. I mean, that's just a logical combination of two statements. If B analyzes this experiment and knows that whenever A saw tails, he's certain about that, and now he's indeed certain that the condition here is satisfied, then he can make this statement. Now the actual critical thing, which one could ask oneself whether it's justified. So this is something that is still operationally verifiable, actually. I mean, this is really not something one should doubt, because B could go to A and ask him, are you indeed certain that W is fail? And A would confirm and say, yes, that's exactly what I've written down. But what B could now do is to say, okay, if this holds, then our classical way of thinking suggests that I can now also be certain that W is fail. So it's just essentially this fact that we can learn from others. If I know that someone else knows that, then I can say, okay, that's valid knowledge, at least if every one of us applies the same theory and the same rules. Now you see, at this point, by the way, A is completely out of the picture. We can, from now on, forget A as an agent. So there's no role A has as an agent any longer. And it's therefore not problematic if we now later have steps where U somehow measures the whole system A, because there's no longer any statement from A expected. So the experiment proceeds like that in a chain. And at the final time, let's say time 4, I don't do time 3, but it's always the same principle. We have the following situation that U is certain, says I'm certain that W is equal to fail. But, and this is why there is a contradiction in the thought experiment, when actually W measures indeed, W measures and gets W equal to OK, which is the opposite value. So the thought, so again, what happens here is the following. 4 parties reason according to rules, which are kind of just derived from quantum theory. So these are rules that are that could also be experimentally verified. As I said, they could go there and verify whether these things are true. But we compose them in a way which is no longer directly verifiable. So that's kind of the critical step, that we go from such a statement to that statement. And at the end, in this particular setup, which is very artificial, but still it's a valid physical setup, we see that the composition of these statements led to a situation where one of these agents make the statements that I'm certain that the outcome here will be fail. Nonetheless, the outcome when W measures will actually be OK. So the conclusion from that is something went wrong in the reasoning. And if we now make the assumption that quantum theory is right and all the predictions that we could in principle verify experimentally are correct, then it has to be that implication here. So in other words, and that brings me to the conclusion of the talk, even if we are certain about things and therefore think that our knowledge is kind of classical in that sense, because we are classical from our own perspective, but of course in this situation from the outside we are not, things can go wrong in the sense that the reasoning rules that we apply in daily life lead to wrong conclusions. And by the reasoning rules we apply in daily life, I mean such reasoning rules like this. Okay, so to summarize what I did is in this talk, I try to kind of convince you that the way we are often thinking about physics, like the Heisenberg uncertainty relation, relies on a more or less implicit assumption. I mean, it's getting more and more explicit as quantum information develops. And the assumption is that the perspective from which we are describing the world is a classical perspective. In other words, that the agents who are making such statements are classical, and that the same statements are no longer true for quantum agents. However, that if they're not, of course they were not wrong technically, they're just pointing out, or they're making clear that there were special cases. And if we now try to generalize them, we see that what is kind of seen as classicality would, in a more general sense, be more accurately described as shareability of information. Because if we, for example, phrase the Heisenberg uncertainty principle in this way, we retrieve it. We retrieve a more general version, which specializes, of course, to the version we are used to in the case of classical information, because classical information is shareable. But somehow the converse is not true. So we could not say that if information is shareable, in the sense that it's, for example, also verifiable in this way here. Sounds like it's verifiable. I know that someone knows that, and I could even go there with a projector and measure it and see that the person really knows that. This is still not sufficient as, okay, typo here, as pointed out or as illustrated by this thought experiment here, where indeed the assumption is that the individual parties are classical in this weak sense that they have their knowledge about other things is knowledge with certainty, but they're not classical necessarily from an outside perspective. But that's true for us in general. I mean, I'm not classical from God's viewpoint. I'm probably in a big entangled state, at least according to quantum theory. I'm not sure. Okay, that's at least in this theory like that. But in the thought experiment shows that this is already a problem. If someone is from if he's classical by his own definition, but quantum from the outside, and at the end we combine statements, we arrive at the contradiction here. So the challenge, which I announced before, is to find a better criterion on when can we still apply classical reasoning. What's kind of a safe criterion that is actually really applicable? It shouldn't be the criterion that we are from the outside in a classical state, because we are not. I mean, we are always probably in an entangled state if you use things from an outside. But what could be a minimal criterion that would allow us to do the reasoning that we are usually doing, like this one, and still get results that are not contradictory? Okay, with this challenge, I would like to end, and I'm looking forward to a discussion. Okay, I'm not sure whether anyone is talking, but if someone is talking, he or she is muted.
I'm sorry, I was muted. So yeah, thank you for your talk, very interesting. And so now is the time for question. And please manifest yourself in the public messages. And the first question is from Alexei. Humble.
Yes, thank you, Renato. Of course, this last challenge that you presented reminds of some of the discussions from quantum logic, but my question will be about this jump from B certain that A certain that W equal fail to B itself is certain that W equal fail.
So this question mark here you're talking about.
Yes, so to me this jump sounds like a matter of trust rather than logic, because somehow B trusts that result from A to be their result. Right, so it's not only a certainty about A, it's more a matter of trust that A is as good as an observer as I am. So to me, this is not a logical statement. This is really a jump that contains a statement of trust.
Yes, I think this is an interesting point to view it from that perspective, but maybe one should then be more, I should maybe be more precise of what the assumptions are of the thought experiment. And maybe I would say, if I make the assumption that a priori the agents agree among each other that they all apply the same rules, so they kind of agree on a set of rules, and they, let's say they are, I usually prefer to think of them almost like computers and then just apply these rules in a rather mechanical way. Then agent B not only knows that A is certain about that, but he would know, okay, A has applied the same rules as I would have done and arrived at this conclusion. Or in other words, if I was in the position of B, I would have arrived at this conclusion, and therefore I trust it. Of course, one could still say this is a matter of trust, because I trust somehow my other me who would have seen something else. And this is indeed probably the question, but it's not a trust in the sense that
I think only classical agents can have this common knowledge. Quantum agents may not have that kind of common knowledge you're talking about. But okay, thank you very much.
But maybe here, okay, that's also something interesting about the common knowledge. I think the common knowledge would only be that they apply the same rules, and everything else has to be explicit. Of course, here one could say, if B can make this statement, that's not common knowledge, because maybe A doesn't know what B knows, but B is at least certain what A has, but the common knowledge is only concerning the rules. So they all agree these are the rules. And Of course, that one could also question whether we can even agree, have common knowledge about the rules of quantum theory. I'm sure we don't at the moment, but a good theory should allow us to do that. Maybe. Thanks a lot for the question. Okay.
Next question is from Philippe.
Okay.
I wrote something in the chat, Renato. Philippe Franchi speaking. You remember we discussed that a lot a few years ago already.
Yes, of course.
So basically, I think your definition of QM that you use in this reasoning is just not QM. It's something else. QM does not work that way. In standard QM, von Neumann's thing, you need to define a level where you make projection, let's say, and you cannot play with this level. Otherwise, you will just run into contradiction, and you do run into contradiction. But what you use as a basis is sort of universal QM, which is simply not QM, whatever you think about. So either you take it formally from standard textbook QM, and it's not what you do is not QM, or you use our CSM approach with Alexia, for instance, where we have context. Contexts are classical, and you do need that to make sense of QM. Otherwise, you just run into sort of a garbage.
Okay, thanks a lot for bringing this up. Yes, of course, I remember these discussions very well. And actually, after thinking about the discussions for a long time, in the meantime, I also start to appreciate your point of view much more than I did in the past. And indeed, there's something I haven't now talked about, which is the assumption on when are the rules of quantum mechanics that I'm applying even valid. And I was just implicitly taking this viewpoint that we can always, from each agent's perspective, apply quantum mechanics to the rest of the world. So that was an assumption. That's, of course, an assumption that is neither experimentally verified, nor do we have other very strong reasons to believe in it, but that's indeed the assumption I made. And I think it's an assumption that is commonly made, and it's an inherent part of many interpretations, like cubism, for example. They assume that there's the agent and the world around is just quantum. And if, for example, that agent describes the world, then this whole thing can be seen as a quantum system. If that agent describes the world, then from his viewpoint, that is a quantum system. Now, I understand that if you have an interpretation, and yours is one of those, or a view on quantum mechanics where you say, no, this is not observer dependent, it's rather that in order for a system to be a quantum system, it needs a context with respect to which it's going to be measured.
Another way to tell it is that quantum mechanics is a theory of isolated systems. What you call a system is quantum mechanics is always an ideally isolated system, but you can make sense of its quantum state only with respect to the outside, and the outside is not bounded. So
yes,
you can describe that if you use algebraic approach, where you have type 3 von Neumann.
But let me maybe say that.
And so it just means that standard type 1 quantum mechanics, standard textbook quantum mechanics makes sense only if you use it within the framework of von Neumann rules. If you want to go outside von Neumann rules, you have to do much more sophisticated things mathematically, and you don't get what you tell. You get algebras, and basically you get context at the end. You get macroscopic commuting observables, which are context. And mathematics, if you use it properly for unbounded systems, does not give you universal wave functions, etc. I will disagree with most people in this conference by telling that. I know it, but this is what I tell. Sorry.
But I mean, it's of course a reasonable view to say that if the agent here wants to talk about this quantum system, then there has to be a context, and the context is, of course, for example, the measurement devices and the agent itself. And if this is a context to that quantum system, then I cannot at the same time treat this as a quantum system. But the point is that you would already disagree at the much earlier point than with my work. I think you would already disagree with most of the descriptions about, for example, with Deutsch's descriptions of the Venus friend experiment. So
Deutsch is every time. I'm not every time at all, as you can see.
Yes. So in that sense, I would say, okay, if you're saying I'm not using quantum mechanics, I'm using of course, I have to make a choice. And the choice is that I'm assuming that quantum mechanics is a valid description of any system from any agent's viewpoint. And I accept that this viewpoint is not shared by everyone, for example, not by you.
I disagree. I know Kaslav also called that universality. I fundamentally disagree with this view on universality. I think quantum mechanics is universal, but not in that sense, not in the sense of a universal wave functions. But okay,
I don't want to actually disagree with that. Maybe I should make my statement more carefully and say that if we make that assumption that I just mentioned of the universality, then we arrive at the conclusion I stated. So you could even regard my result actually as a confirmation of what you're saying and saying, okay, we are running into so many problems, into this disagreement here, that the assumption that we started off with, namely the universality of quantum theory, must be wrong. So in that sense, I wouldn't want to contradict you. It's more, let's say, a logical thing, a logical statement that if we make this assumption, then we arrive at whatever I said. And I think I should have
I don't
made
say,
it more clear that I made this assumption.
Wrong. I say naive universality, this kind of extending wave function to the whole universe, which is type 1 quantum mechanics, is simply does not work. But von Neumann told that already in the 39 paper. So why are we still trying to extend type 1 quantum mechanics to everything? It simply does not work. It is well known, and you prove it. We discussed that also when we discussed. My conclusion about your talk is that your thing is supporting my point of view. Okay.
Yes, I mean that's a valid point of view, as I said. As I said, I'm starting to do things. I mean, also when I look at, for example, Czeslaw Bruckner's work on quantum reference frames, it also, I think, reinforces my, let's say, belief that the way we are using quantum mechanics is very restricted. And in general, if you take into account other things, for example, that reference frames are also physical systems, we have to change something there. But yeah, that's of course something I don't have an answer to. I'm just trying to make the point that I don't find this unreasonable to doubt the universality, although I still find it a good working assumption. And then, of course, we may come to the conclusion that indeed it was wrong.
Okay, thank you for the discussion anyway.
Good. Next question is from Kaslav.
Hi, Renato.
Hi.
Thanks a lot for the talk. And it was very clear. Maybe just a reference to the previous question by Felipe is that we don't need to assume the wave function of the universe. You know, your example is always a wave function for some observer. Right. So, and so it really nicely shows that if you talk about knowledge based on observations, then one should be careful in quantum setting to take the knowledge of other observers as your own knowledge. And now you pose this challenge, and I don't know how to address this challenge, but it's obviously that in all these examples, the measurement of observers' memory or context or environment is really important. It's a kind of different type of the measurement than in usually standard non-Wigner situations. Now, what I would like to clarify is your notion of quantum knowledge that you used before that in example of just as a very beginning when you talk about observer being kind of entangled with the system. And then you mentioned that in a sense, this observer quantum agent could have a knowledge about complementary observability at the same time, because it's a kind of EPR entanglement that can be written in many different bases. Now, there are two possible ways of understanding this quantum agent. One would be exactly the one that I mentioned and that you proposed. It's a kind of internal view. The other possible interpretation of pure entangled state that you write down between the agent and the system is a description of yet another external observer that can simply confirm correlations once the measurements are performed on the agent and the system, and have nothing to do a priori with the knowledge of internal agent, namely that this internal agent still has just knowledge about one observable, but not both at the same time. So can you comment on this distinction, and why would you prefer one or the other?
Yes, Okay, and this also relates, of course, to the question that Nicolas Gisin asked during the talk. What does this knowledge mean? I'm not sure. I mean, this is something that bothers me since quite some time. Actually, it also is of practical relevance, by the way, in cryptography, because in cryptography usually are on the safe side and assume that an adversary is exactly an agent with this quantum knowledge, so to speak. So I think the operational claim that I mentioned already before, which is just if I went there and asked the agent, do you know X? And he could give an answer with probability 1. That's probably the undisputed part. That's just what we could prove. Now, I think my problem is a bit, I mean, my problem with giving another description is that as soon as I want to somehow give a description of what it means, I already implicitly bring in again some classicality by asking myself, what if, for example, I now measure from the outside or so. So somehow it's very difficult to really stay on the quantum level. But if you're taking this notion seriously and they're saying agents are now really generic quantum systems, they don't have to, for themselves, do a measurement of their memory. They are just quantum. That's all they are. Then all our, let's say, intuition about this somehow fails. So my answer is still, I simply don't have an intuitive explanation. So the only thing I can really say is that I really restrict to this completely operational viewpoint and say knowledge of something means that I can answer a question about that with certainty. And all the other things are somehow always bringing me back to someone comes in and tries to make this knowledge again classical and then reason about it. But this seems to be somehow the wrong approach, because if you want to characterize quantum knowledge, why should we bring it back to classical one? So unfortunately, I really don't have an answer in that sense, except for this operational characterization. And that's also why I couldn't give maybe a satisfactory answer to Nicolas' question, but I think it's an interesting question. But maybe I should briefly also comment on the other point you mentioned, that the agents are measured. That's, of course, true. We run only into the difficulties because, for example, this agent A is measured by another agent. But it's just important for me to comment on this, because this was also something that Scott Aronson pointed out many times and always repeats, that it's not surprising we have a contradiction here, because the agents are measured and we shouldn't measure agents. However, I think what is important is this timing here. So as I said, at this point, when we are at time 2, the agent A is completely out of the picture. So from then on, everything that continues in the reasoning does not involve agent A. Of course, agent A had a role to arrive at this statement. He appeared here. But once the statement is made, we can forget about A. A could die, if you like, and be burned, and then it shouldn't. Of course, if this guy is dead and now this guy measures the ashes of it, that shouldn't have an influence of whatever happened. So in some way, if we want to say, okay, the problem was really that this agent was measured, and try to come up with a kind of theory that does not run into this problem, we would have to always keep track of where the memory comes from. So if I know something and I realize this knowledge I have only because some other agent, who is dead since 200 years or so, had the knowledge, then I should no longer trust this knowledge, because this agent now is maybe no longer in the basis in which he derived the knowledge. So I just want to start and kind of state that saying that, okay, the problem appears because we measure this agent is, for me, not a satisfactory explanation to say I shouldn't worry about this, because the measurement really is about, happens long after the agent somehow had a role in the whole statement, and I already have somehow so in other words, I have extracted here the information from A and saved it to B. B now knows what A knew, and now A can go, so to speak. So I just want to say this is more subtle in that sense, so there's not like an easy way around it by saying, okay, let's not measure agents.
Thank you.
Thank you. I think unfortunately it's the time for the short break, and there is a lot of questions remaining. So maybe we can just continue the discussion here for those that want. So the next question is Ipo, then Alex, Lev, and Aurélien. So I suggest you that you can continue here, but we will start the next meeting at 10:20.
Yeah. By the way, I forgot to thank Gerard for his flexibility in swapping the talk. So I really want to thank him for that.
Okay. And I thank you again for your talk and your participation.
So I guess I can ask my question.
Yes, please.
Thank you for the talk, but I guess you already kind of partially answered, so it will be quick. I just wanted to ask you if you think that your result can just be interpreted as the same no-go theorem from chess level, like observer independent facts. You have some kind of no-go theorem against observer independent facts, or as you explained to Philippe in some kind of way. It's just that you cannot have, your results could be interpreted as you cannot have an absolute quantum agency, and quantum agency is kind of relative. So you cannot say A, B, and their friends are all agents at the same time. And you just need some kind of agency frame to describe your answers. And another question also. So would you say that, because I know that a lot of people say that, and sometimes I do it also, would you say that your result is just some kind of RD paradox mixed with beginner's friends, or is there more to that? Because I know that a lot of people just consider it as this is RD paradox that is beginner friendly, or I don't know.
Okay, maybe I start with the last question. So maybe I could say yes in the following sense. So actually, I should say this thought experiment really combines ideas, first of all, obviously from Wigner's friend experiment, also from Deutsch's extension of Wigner's friend experiment, also from Bell experiments, also from Hardy's experiment, and also from Jaslav's experiment. So it's somehow a big combination of experiments. So you could say it's just that. So some people sometimes say this is just Wigner's friend experiment, and then others say this is just Hardy's experiment. So maybe the fair thing is to say it's a combination of those. But I think this is not the important thing. The more important thing for me is the following, that it asks a different question. So the question that is usually asked is the question of, is there, for example, a hidden variable or so? Here the question I'm asking is there a consistent way to describe agents who are themselves, so can I use quantum theory to describe agents who are themselves using the theory? I think this is kind of the new question that is asked. I mean, new, that was certainly not Hardy's question if you compare to that. So the question, and this is a consistency question I could ask for any theory. I could also do that in thermodynamics, for example. I could ask myself, if I, for example, describe an agent, and this is actually almost done if you look at Maxwell's demon. So if I describe an agent who is itself applying thermodynamics and reasoning about the system, do I somehow get into contradictions? And clearly, and if you assume that the theory is universally valid, and this was the assumption I briefly discussed before, of course, with Philippe Grangier. So if you make this assumption that quantum mechanics is universally valid, then it should satisfy this criterion, or any theory that is a theory of the world should also be able to describe the agents who are using the theory, because these agents are obviously also part of the world. So I think this is really the new aspect. And then it's not so relevant for me, is it now Hardy's or Wigner's friend or Bell's experiment? I think at the end, it's just a thought experiment which shows that if we want to do that with quantum theory, then we run into troubles. Now, I also know that, of course, there are different then conclusions from that. And that's why I want to make the statement somehow as interpretation independent as I can. But of course, in doing so, I have to make assumptions. And as I said, one assumption is that we have this universal validity in the sense that any agent can apply quantum theory about the rest, on the rest of the world. And I think this is another aspect, that somehow the assumption is not something about hidden variables or so, it's really just the assumption about, is the theory applicable from the viewpoint of agents? And I think there's an interesting question then how this, for example, relates. I mean, I just see Weidmann on the right of the picture. How does it relate to many worlds? Because there we generically don't have this view. In many worlds, we say, no, the correct view is always the view from the outside. So one could say, in this whole analysis, I'm already not talking about many worlds. But then I think another aspect which is important to me is that one could take a kind of, again, an operational perspective and say, whatever the view is, I should be able to come up with a consistent set of rules that allows an agent to reason. And the rule could be, yeah, now you should take God's perspective and analyze it from the outside, and then make a prediction. And I think the challenge then is just really write down the rules. And that forces people to be very precise. So if people are vague and say, okay, from the outside we have to define branches of the world, but I don't know what exactly the branches, it's just something vague, then they cannot write down the rules. So it's somehow, for me, a way to force people to really be precise about what they mean when they talk about quantum mechanics, rather than trying to push one of the interpretations. So in that sense, it's really a difference to these Hardys and Belsings, which try to make the point that there is no hidden variable thing. So I think in that sense, the summary of my answer is the purpose is certainly a very different one from these other experiments. The purpose is to ask ourselves, can quantum theory be applied to users of the theory itself?
Okay.
So that was your second question. Now,
yeah, that was the second.
Yes.
My first was, so could you compare it with Časlav-Nogo theorem, or?
Yes, yes. So I think they're closely related. I mean, of course, the aspect now I just mentioned is probably something that is a very different starting point, because I think for Časlav, as far as I understand, but Časlav has to correct me, that the question was really, are there observer-independent facts? And for me, the question was really, can quantum agents describe other quantum agents? Now, this has to do with each other, because clearly if I have a situation where I say, I'm certain, so an agent is certain that another agent is certain, this is certain. So if there are observer-independent facts, then this implication is certainly justified. So I would say, in that direction, there's a clear connection that, let's say, if you assume now the thing that Časlav proves is not true, namely observer-independent facts, then there is no trouble in applying this implication here. Conversely, I'm not sure, so it doesn't go in the other direction, because Časlav can, of course, so if you assume observer-independent facts, you can even make statements when no agent is ever certain about another agent's thing. So, for example, in Časlav's experiments, it's all probabilistic knowledge, and so we never have statements of that type. So, in order to extend my thing to Časlav's, I would need to come up with a rule which tells me if I'm 98% sure that this value, that the other person is 97% sure of something, what does it mean? So in that sense, there's not a one-to-one link between the two, but they're related, at least in the way I tried to sketch now. But maybe Časlav has some other comments.
I can agree with this. I think that my no-go theorem can be easily extended to GHZ argument, in which you have deterministic statements still. And I feel that there is a difference in which you talk about facts of the world, and then you read out or have some ignorance or knowledge about these facts, and talking just about the knowledge. And it seems the second is weaker in a sense.
Yes.
But when you look at the proof itself, in order to collapse this knowledge and to be used by a single observer, at the end, what you use is just Boolean logic, which is a classical logic. So I feel like on the level of concepts and the question, it's independent. The level on the proof is very close to each other. But
right.
Yeah,
yes.
I agree
Right.
with what
Yes.
Renato
Okay,
said.
it's good. So yes, indeed. So I didn't. You see, I never talk about facts. They're always kind of statements an agent makes about about knowledge somehow. So all is knowledge. There don't need to be facts in that sense in to phrase these statements. I think that's one conceptual difference. Okay.
Thank you.
Thank you for the discussion. I think it's time to go to the next speaker now. So thank you again,
Okay.
Renato.
Thank you as well. It was a pleasure.
So we will now listen to Christopher Timpson. Christopher Timpson is a fellow and a teacher in philosophy at Brasenose College and a lecturer in the Faculty of Philosophy at the University of Oxford. And today he will talk about cubism with a talk on